All right, so yeah, that's what we looked at last week, and this week we're going to pick up, or 2 days ago. Now we're going to pick up with, we looked at callbacks, we didn't look at recursion. So for those of you who've never been exposed to recursion, recursion is just a function that calls itself, kind of a trippy concept, right? But here I have a function being, well, let's just look at a simple function. All right, so here I have a function greet, and function greet's being called inside function main. Here's a really novel idea. Could I call, instead of inside function main, I'm calling greet, right? Inside function greet, could I call greet?
Yes.
Whoa. Right? And what's that going to do?
Recursion.
That's recursion. Because it's kind of like this, it's almost like an infinite loop unless you build it correctly. Because greet's going to run, it's going to call greet, which is going to make greet run, which is going to call greet, it's going to make greet run, it's going to call greet, it's going to make greet run, right? So that's recursion. And you could use that to solve some problems. So recursion is more of like a computer science, novelty, and not so much something that you use in production. Because recursion is really expensive in terms of performance. And you could always solve anything you do with recursion. You could solve it some other way with loops. And so, it's just nice to know about recursion. And it's something, if you study computer science, you'll work with a lot just because it's a novel concept, right?
Yeah, the computer science teachers,
they love it, dude.
They love it. They love talking about recursion.
Yeah. So they love recursion. But in actuality, it's not that performant, right? Because what happens is we have the stack. And every time you call a function, it gets put onto the stack. And so the stack, there's the stack and the heap. And so the stack is like what the computer needs to remember to run. And so if I have, function 1, which calls function 2, and then function 2, which calls function 3, right? Here's main, and then main has function 1, which calls function 2, and then function 2, the stack just grew, and then function 2 executes and returns, which sends the value to function 1, which then finishes and executes and returns, which goes back to main. So it's this stack that goes up and out, up and down. So it's last in, first out. The last one in was F2, that's the first one out, right? And so it's just this building thing of what I have to remember, and now I'm executing and bringing it down. So when you do recursion, it just keeps throwing functions onto the stack, and the computer's having to remember that. So that requires resources. And then the heap is like taking it out of this flow of I could throw it away and putting it over into a big pile where I might need that at some later time, right? And so it's like kind of like something else might need that than this one process which is running. And so that requires, that's another performance hit. So things going to the heap is bad, right? Adding too much to the stack, not so good. You want to keep things on the stack as much as possible, and then if they, and try not to send them to the heap. And that's like, the extent of my understanding of that. So I'm still learning about this area myself. But, the heap is where garbage collection runs. So if I have a variable whose scope is F2, that's staying on the stack. But if I then put that variable up at the package scope and have other things accessing it, it's got to go to the heap because I don't know if that's going to be needed again at some point. And then the computer has to run through everything in the heap and check, is anything needing this? And that takes time. That's the garbage collector. All right, so recursion. Recursion has a cost. And this is what recursion looks like. So we have func main, which is just going to print factorial 4. So factorial is the number times 1 less than the number times 1 less than the number. So factorial 4 would be 4 times 3 times 2 times 1, right? Or 24. 4 times 3 is 12, times 2 is 24, times 1 is 24. And so what we want is, we want something that, so the way this works, right? We pass in an int. This is an unsigned int. So it's only positive, there's no negative. And we're passing in 4. And is 4 equal to 0? No. So we're going to return 4 times factorial 4 minus 1. 3. Okay, cool. So we have 4 times, and now this runs and executes, right? Another function. And that means, hey, is 3 equal to 0? No. So we have 4 times, and then that becomes 3, right? 4 times 3, and then this becomes factorial 2 minus 1. So then it comes and runs again. We have 4 from that first one, 3 from the second one, and then this time around becomes 2. So we have 4 times 3 times 2, right? And then 1, right? And then it runs again. We have 4 times 3 times 2 times 1, and then 1 minus 1 is 0. And it runs again, and it says, hey, return 1, right? Okay, so it returns 1, and I just hit the wall. Because that takes me out of the function when it returns 1, right? But then this returns 2. Those all unwind somehow, and they return, yeah, because the very first function. So this gets me out of this iteration of the function, and then the very first function, those all start to unwind. So I added all that stuff to the stack, right? And then chunk, 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 chunk. They all start to decompress. How many people see that? How many people don't see that? All right, let me get a pen. I don't have a pen. Let me see if I could do it with a just right here so that people. Oh, yeah! I love it. That's good teaching right there. That's good preparation, right? I'm going to applaud for myself.
My teacher has a good way of explaining this. He uses a little like box, and he puts the kind of like that actually.
So the first time through, we have factorial 4, right? This is this one. And so that returns 4 times factorial 3, correct? And factorial 3 returns 3 times factorial 2. And factorial 2 returns 2 times factorial 1. And factorial 1 returns 1 times factorial 0, right? And factorial 0, if x equals 0, returns 1. So, when these unwind, it's you could write it all out like this. Oh, I need to be in edit mode. Hold on. You could write it all out like this. So that's one way. Here's another way. You could write it out like this. So, right? Returns 4 times factorial 3. Well, what's factorial 3? Factorial 3 is 3 times factorial 2. Well, what's factorial 2? Well, factorial 2 is 2 times factorial 1. And what's factorial 1? Well, factorial 1 is 1 times factorial 0. Well, what's factorial 0? Factorial 0 is just 1. Did that make sense, seeing it kind of execute, right? It's just substitution.
What are the two, un?
Un is an unsigned integer. So when we look at when we look at Golang spec, we have types, numeric types, and here are all the numeric types, and that's kind of overwhelming. When I first started learning Go, I'm like, really? And there's going to be a time when I need an int 16 as opposed to an int 8? Can I just use an int and you figure it out? What's a rune? I don't know. So, that kind of was a little like, okay, when I first started this language. But really all we do is we use int most of the time. That's it. That's plenty good for us. And int is the same size as a uint. And a uint is either 32 or 64 bits. And it is implementation specific. That one little phrase right there, from that, if you were computer level genius, you would know that either 32 or 64 bits, you would just go, oh, that's based upon the word size of the architecture. Which means if you have a 32-bit computer, your int is going to be 32 bits. If you have a 64-bit computer, your int is going to be 64 bits. Take advantage of the full word size, and word size is how many zeros and ones can the CPU process at once.
What if you wanted to return a decimal number?
Float.
Float?
Yeah,
float 32 or 64?
64 just, yeah.
So you would just write float?
Float 64.
Oh.
Float
It's
64.
not a regular float.
Yeah, no regular float. Float 64. Yeah, it is interesting. I'm not sure why, and there's a dang good reason for it being that way, I'm sure.
But we don't know.
But I know I don't know it. But I have faith in Jesus Christ, Buddha, Allah, Rob Pike, Ken Thompson, and Robert Gressmer, and Google. I have faith in those individuals and institutions. Well, corporations and individuals, so. That's a quote right there. I got to send up the chain somehow.
Google is no longer a corporation.
Really? Sole proprietorship?
You gotta look it up though. I don't want to like.
Is it like, is it moved to the phase of deity?
Yes, but that's not related.
We don't want to be a corporation because we are not an individual. We are a deity. We are computer gods.
Aren't they called Alphabet now?
Yeah,
Oh,
and Alphabet Inc. owns Google and other like things that Google used to own. So, like.
I'm sure it's got
The
some.
G in the alphabet is Google.
Yeah, Google is just like the web cloud stuff now, really. Like,
Do they own the United States government yet?
they should.
They should. They'd be doing a better job. They would shuttle us all to work in driverless cars.
Work. Why would we go to work? We can just do everything from our desk.
Well, those people have to show up to cut our hair, and lunch has to be ready at noon. So
Robots.
somebody's got to be doing that stuff. So uint is unsigned. So you can see unsigned will give me 0 to 255. 8. Unsigned 8, because with 8, we have 200. If we had 1 bit, we could store 2 messages. If we have 2 bits, we could store 4 messages, right? All on, all off, 1 on, 1 off, or vice versa, the other orientation, right? So that's with 2 bits. With 8 bits, and the formula is 2 to the power of n, right? So 2 to the power of n, 2 to the power of 8 is 256. So 0 to 255 is 256 possibilities, right? So with uint 8, we're storing a byte. It's 8 zeros and ones. There's 256 possible combinations. If it's unsigned, meaning there's no positive or negative sign, it could go from 0 to 255, because that's 256, right? The first one's 0. And if it's signed, it could only go from negative 128 to 127, right? Because you got the negative side and the positive side, and that's 256 possible things we could encode. It all comes down to zeros and ones. Unless you're quantum computing. I don't know what that does. It's 0, 1, and 3
Qubits.
qubits.
0, 1, something in between.
0, 1, and something in between.
Is it inefficient to use the wrong one? Like you just always use N64? Is it inefficient? It's like, say you're only going to be working with numbers like 10 through 100 or whatever.
If you know that you're going to only be using a like small range of numbers, then it's good practice, I think, to do that. But you don't have to because it can be really confusing.
Yeah, don't even stress it at this point.
Yeah.
Like maybe in 3 years, you'll like split hairs on that, but it's nothing to worry about right now. You know, the main thing is like, don't worry about performance. The Google engineers and the Go engineers who made it took care of all that. All you need to worry about is writing good, clean code and following Go idioms, like the correct, design patterns for writing Go programs. And if you write good, clean code, your stuff's going to be way fast enough. And if you get to a point where it's not fast enough because you have that many users, you're going to have enough money to hire people to come in and, figure out what needs to be tweaked to get those extra little nanoseconds. That's what it comes down to. All right, so that's recursion. And this is called the base case in recursion talk. You can always use loops to solve any problem that can be solved with recursion. Loops are more performant than recursion. And then defer is something we could use in our functions. And when you have defer, like right here, I've said defer world. That means I'm going to run this at the last possible moment before the function it's in executes, right? So I have function hello, which prints hello, and function world, which prints world. I call a world first, but I say defer, which means it's going to run at the last possible moment before func main exits. So it runs hello first, and then, oh, I'm about to exit, func main says, better run defer, and then it runs world, so it prints hello world. And so defer is really useful, right? There's no defer, it just prints world hello. But defer is really useful for things like closing files. You open a file, you got to close it, right? You take something out of the toy box, you got to put it back. You open a bunch of files on your server or on your system, and you just keep opening files and you never close it. You know what happens. Like, you've done that before on your computer. Like, if I just keep opening tabs, like, that's all taken memory. And if I go to activity monitor, right, I could see, Chrome, right, like, how much performance hit am I taking? Like, right now I'm at, 3.3% CPU.
Hit the memory tab. Next tab.
Memory tag. There we go. That's good. 208 megabytes of memory. Thank you. And, right? 209 megabytes. So pretty light, but I went up a little bit. But did this grow up? 27%.
Start opening like
Because I started, it has to process all those requests, right?
you open something in them.
So you don't want to just open. That's awesome.
That's awesome.
You don't want to open a ton of files and never close them. So when you open a file, as soon as you open it, right next to it, you can just say defer close, right? And that way, when this function exits right here, it's going to close that file. And that is right next to where this is written. So you don't have to be like, oh crap, scroll. Did I ever close that file? This is the Go idiom. This is like the design pattern, right? Keep things as close as possible. Make it as readable as possible. Code shouldn't be confusing. It should be a story that you're telling, that you read this code from top to bottom and it tells you a story, right? That's Bill Kennedy. He says much more about it and talks about words and pages and memory. But so so if we close right here, if we return from the function here, f will be closed when we return here. If we return there, f will be closed when we return here. I mean, this language is awesome. And this is based upon like absolutely zero experience with other languages. I've had some experience with Python and Java. You heard me rail on Java. Was I a little bit hard on you guys? Nobody said goodbye when they left. They're just like, okay, I'm out of here.
No, it was a good time.
I gave the general patent lecture on classes. Had them write down if they could write 72 in hexadecimal, write it down on a piece of paper and hold it up. Otherwise, write a big fat 0 and hold it up. Let me see what you know. And then we did base 16. Because that came up at some point. Were you in the Java class too? No, I didn't think so. Defer. So here's the way it talks about Go's defer statement schedules a function call, the deferred function, to be run immediately before the function executing the defer returns. So that could be like, a mind tripper the first time, to be run immediately before the function executing the defer returns. But you just saw how that works. It's an unusual but effective way to deal with situations such as resources that must be released, regardless of which path the function takes to return. The canonical examples are unlocking a mutex or closing a file. I love that in programming they use this word canonical, right? Like canonical is like, makes me think of monks, right? According to or ordered by canon, law, right? The canonical rights of the Roman Church. Whoa, this is like ordered by God. See, it's coming back to that thing, Google, deity, right? This is ordered by God that you close mutexes and files. Included in the list of sacred books. All right. And the language spec is a sacred book. People will be worshiping this in 1,000 years. They'll get it all confused, and they'll be going to church and worshiping Go. The prescribed official dress of the clergy. Right? It's like how you're supposed to act and behave. That's the canon. A deferred statement invokes a function whose execution is deferred to the moment the surrounding function returns, either because the surrounding function executed a return statement reached the end of its function body, or because the corresponding Go routine is panicking Defer statement, defer expression. So that's how you'd write it in Bacchus-Nor form. I don't say that right, but. And the period means that's the end of the BNF. The expression must be a function or method call. It cannot be parenthesized. Calls of built-in functions are restricted as for expression statements. So expression must be a function or method call. This expression right here must be a function or method call. It cannot be parenthesized. Parens, parentheses, parens, we have curly braces, we have brackets, we have parentheses. So it can't be parentheses. I have no idea what that means. Calls of built-in functions are restricted as for expression statements. So a function that was built in maybe or restricted, I don't know. So some of that stuff's still lost on me. So here's a little bit on the stack. We already sort of saw that. I don't totally understand the stack and the heap. I have more of an understanding than I did 2 weeks ago, 3 weeks ago, but hopefully you can kind of see from this little diagram, right? Functions are built up in a stack. Suppose we had this program, right? Here's the program. Func main calls function 1 calls function 2 calls returns 1, right? So this returns 1, and then 1 ends up here, and so that returns 1, and then 1 ends up here, and then that prints it. So for it to finally print, it has to go all the way through this, and then all the way back. You see how it like, goes through it, and then unwinds it. Like, okay, I call this, I call this, I call this, I call this. Okay, now it returns this, returns this, returns this, returns this. Okay, now I can print, right? And so that's this a visual diagram of what the way that's happening is main calls F1, right? And then we have main with F1 that needs to run on top, and then F1 calls F2, and then we have F1 with F2 that needs to run. F2 returns, and then F1 can now return, and then main can do what it wants to do. Right? So it's this stack that kind of grows, and it's last in, first out. And so that's like an accounting term, but the last thing that came in is the first thing that goes out. That's why it's a stack, right? You stack things on top, and you don't take things off the bottom. You have to take them right off the top. And as you take them off the top, it like finishes. And so that's why we call it, or that's why it's called a stack. You're stacking things on top. And it's last in, first out, because the last thing in to the stack was F2, and that's the first thing out. And so that all takes memory. That all takes memory. And prior to Go 1.3, it used to be non-contiguous stacks. So the stack would have an allocated size, and if you filled that up, it'd just create a new stack, and the last entry in the stack would point to the new stack. And if that one filled up, it'd create a new stack, and the last entry in that second stack would print to the first entry on that new third stack, right? And it's like, okay, that's cool, until right at that little point between stack 1 and stack 2, where, if we ran out, we were no longer using stack 2, it'd collapse, and we'd just have stack 1. But then if we needed stack 2 again, it'd rebuild. Right at that point, if you happen to have a function which was recursive run, you got this incredible hit to performance, because it would do all of the generating to create stack 2, right? And then run it, and then the recursion would pull something off the stack, so it'd throw away stack 2 and just go back to stack 1. And then it'd be like, wait, we're recursive, I need stack 2 again, and rebuild stack 2. So every cycle of the recursion, right at that sweet point, if that's where it ran, is building, destroying, building, destroying, building, destroying. And so now the way they do it is they have a contiguous stack where the stack's so big, and then if you need another one, you get one that's like twice the size, and everything from the first stack gets copied into the top half of the new stack, and then you have all that room at the bottom, and you throw away the first one. And you only have one stack at a time. There's no, and point to the next one, point to the next one, point to the next one. Right? That's kind of interesting, just the implementation details. Like I said, sometimes I feel remedial. There's like a lot to know, right? If you're just cutting your teeth on programming the stack, whoa, you got to learn that now to understand the internals of this language. So you can learn more about functions by following this link that takes you to Caleb's stuff, I'm pretty sure. I'll come back. And let's defer, recursion, the stack. There's some exercises here for you all to do, so let's do something. And Let's do these all together. So what's variable shadowing? So variable shadowing was like when we have, variables in different scopes with the same name. So here's variable shadowing, right? Func max. So we call func max, and then we print the function. So that just gives us his address, and then we call it and get the result, and then we print the result. But if we were to try to call that function again here, we couldn't, because now max is something totally different, right? So that's shadowing. That's bad practice. What is a func expression? Newtown func you up.
Is that where you call a variable and then name the variable a function?
Yeah, right here, right? So we're just assigning a function to a variable. An expression is like, mathematical expression, 2 + 2 = 4, y = 7, mathematical expression. That's helped me to think about expressions like, hey, what's a mathematical expression? Y = 7, that's a mathematical expression.
Lambda expression.
Yeah, so it's setting a variable equal to a function. And if you're in the Java world, Carson's saying we would call that a lambda expression. Is that what they call it in Java?
Not just Java, but that's like the word I always hear.
I've heard lambda. I don't know what it means.
I don't either. I just know that's what it's called. Well, actually, lambda is the I want to get into it. Keep going.
Yeah. So what is closure? One thing enclosing another, right? And helps us sort of limit the scope of something. So one thing enclosing another. So here is func main encloses func increment. Right, here's func main, and it's enclosing func increment. And the better example of closure, let's see, hold on. This is cool. Right, there's the closure example where make even generator. So here's a func expression. We're taking next even and setting it equal to a function. So that's a functional expression, a func expression. And make even generator has this variable here, and then it's returning a func. Okay, so it's returning a func. So this function is enclosed within this function. So here's enclosure. And whenever this function runs, right, it's referencing I, which is in the scope of the outer function. But because the scope's outer function, and this is inside, this inner scope also has access to the outer scope. Just like if you had something in package scope, every function would have access to something in package scope, because the outer scope is kind of enclosing the inner scopes. So here, this outer scope, right? This is an inner scope, but that's still available because it's in the outer scope. So as we call next even over and over and over again, so we get a function, and then this function just adds 2 to I, maintains, here's where I, the state's maintained. And it's only running in here every time we call next even, because this is the function that came back to us, right? So this is the only code that runs, but this is getting incremented and stored. The value of I, the memory address, as we change it, it's changing it and keeping it. It's kind of interesting. So that's closure. And what is a callback? Passing a func as an argument. Great. So let's look at a callback. Func you up, Newtown func you up. Passing a func as an argument. So this is the diagram that works. That's the call to visit, the visit function. It takes 2 arguments, slice events and a function, right? And there I am passing in a slice events and a function. And so that red highlighted area is my second argument to the call a visit. So that's a callback. And then I just call that function inside, the function that received it as an argument. Who wants to go have some beers? I say class is over. There's a callback. So these, I think, are some really good concepts in programming just to nail down, because you'll see callbacks in JavaScript, right? You'll see closure. You'll see func expressions. Last night or 2 nights ago in Bonnie's Java class, we were talking about variable shadowing. That was like in Tony Gaddis's chapter 6 of Java. So we know how defer works, and we kind of have a little bit of an introduction of what the stack is and how it works. And, just to start thinking about that. Plus a little bit of the history of how the stack was implemented, the implementation details in Go, and how it is implemented now. So let's do some programming, and let's do that. 2 returns.